Okay, let's finish this topic of sampling and reconstruction with some examples. Let's start saying that we have a sinusoid. Let's say we have a cosine with a frequency of 300 hertz. We're going to sample it with a sampling frequency of 2 kilohertz, 2,000 samples per second. When we say it's sampled and then reconstructed, and the reconstruction filter, the low-pass reconstruction filter, has a cutoff frequency of 1 kilohertz. What is the output of the sampling and reconstruction? So our cosine is going to have its spectra. If you remember the spectra of a cosine, wonderful. If not, pause it, go back, review it, right? This is not part of DSP. This would be the Fourier transform of a continuous time cosine, right? It's going to be two impulses, one at the frequency and one at the negative frequency. We're using radians per second instead of samples, or instead of hertz, instead of cycles per second. So a frequency of 300 hertz, if we change it to radians per second, it's just multiplied by 2 pi. So the frequency would be 600 pi radians per second. So we're going to have an impulse at 600 pi and one at minus 600 pi for our cosine, right? This is the spectra of the original signal. We're going to sample it, and we sample it at 2,000 samples per second. What does the spectra of the sampled signal look like? What I'd like you to do, as I had mentioned before, pause the video, sketch it out, do it. Okay, now that you have it written out, we know what it's going to look like, right? We know that the relation between the discrete time frequencies and the continuous time frequencies, right? Omega is omega over f of s. This is going to be our relation when we sample signals. And so we see that if the sampling frequency is 2,000 hertz, a frequency of 600 pi radians per second will be a frequency of 0.3 pi radians per sample after sampling. Minus 600 pi would be minus 0.3. We know, since it's sampling, it's a discrete signal and it's going to repeat every 2 pi. So we could just take this and repeat it every 2 pi. 0.3 pi, we shift it by 2 pi, it's going to be 2.3 pi. Minus 0.3 pi, we shift it by 2 pi, and it would be 1.7 pi. This will go on to infinity. We also do it on the negative side to get the spectra at minus 1.7 pi and another impulse at minus 2.3 pi. So this would be our sampled signal. Now we're going to reconstruct the signal. In other words, we have to change it from radians per sample back to radians per second. Now, of course, we use the same equation except we solve for capital omega. 0.3 pi turns into 600 pi once again, and 1.7 pi is 3,400 pi, 2.3 pi is 4,600 pi, and so forth. And so we've changed, and we have our continuous time signal, but we have the repetitions that we need to get rid of. We have a low-pass filter, and the problem tells us that the low-pass filter has a cutoff frequency of 1,000 hertz. Now, since we're using radians per second instead of cycles per second, right, 1,000 hertz is going to be 2,000 pi radians per second. And so we get right, if this is 600 and this is 3,400, let's say 2,000 pi is more or less here. And so we have a low-pass filter that's going to eliminate everything after 2,000. It's going to let everything through from minus 2,000 to 2,000 pi. So this, after passing through our filter, is just going to be equal to this. So we get the exact signal out that we got in. Now let's go back and let's repeat the problem. But let's say that the sampling frequency is 1.3 kilohertz. Okay. Oh no, I'm sorry. Repeat the same problem. What we're changing is the frequency of the cosine. Instead of being a frequency of 300 hertz, let's say the cosine has a frequency of 1300 hertz. And let's sample and reconstruct it. Now, as I had mentioned previously, to avoid aliasing, the sampling frequency has to be more than twice the highest frequency in the signal. In the previous example, it was fine because, right, the frequency of the signal is 300 hertz, the sampling frequency is 2000 hertz, right? Twice 300 is 600, so there's no problem, right? 600 is less than 2000, so there's going to be no aliasing, and so that was why we were able to recover the original signal again. Now in this case, the highest frequency in the signal is 1300 hertz. The sampling frequency is 2000 hertz, right? So twice the highest frequency is going to be 2600 hertz. And so the highest frequency in the signal is higher than the sampling, twice the sampling frequency, and so we're going to have problems here. Right? We need the sampling frequency to be higher than twice the highest frequency of the signal. Doing the similar thing that we did before, 1.3 kilohertz is going to be 2600 pi radians per second. And when we sample it, that's going to turn into 1.3 pi radians per sample. Again, what I'd like you to do is pause the video and sketch out what the spectra looks like after sampled. Now what does the spectra look like? Well, these two, when we sample them, it's going to be an impulse at 1.3 pi and minus 1.3 pi. And those are the spectra for k equal to 0. Now we know that it's going to be shifted by multiples of 2 pi. So if we shift this by multiples of 2 pi, what do we get? Minus 1.3, we shift by 2 pi, we get this term here. If we shift this by 2 pi, right, we're going to get this term up here. Okay, I noticed that there was an error with the colors I had used. So we have these two impulses are going to be the impulses in red at 1.3 pi and minus 1.3 pi. Now when we shift by 2 pi, this is going to shift to 0.7 and this one will shift to 3.3. So these will be the two impulses corresponding to the first shift by 2 pi. If we do another shift by 2 pi, this one of course is going to shift here and we'll have another one up even higher. We have to shift in the other direction too, so if we shift to the left, this impulse is going to end up at minus 0.7 and this impulse at minus 1.3 pi is going to end up at minus 3.3. And so this is the spectra after sampling of the original signal. When we go and reconstruct it, right, we use our same formula here. We get our frequencies. Of course, we have the original spectra at 2600 pi, but we also have other spectra. In this case, because the sampling frequency was too low, we actually have overlap of these spectra. Now, when we have our low-pass filter at a frequency of 1000 hertz, of course it's going to cut out all these spectra, including the original spectra, and it's only going to let through the impulses at plus and minus 1400 pi. So these are the impulses that it would let through. Now 1400 pi radians per second is a frequency of 700 hertz, indicating that there was aliasing. We don't get the same frequency out that we got in. And this is why it's called aliasing. Alias, you know, it's one thing masquerading as something else. So the original frequency, which had a frequency of 1300 hertz, is now looking like a frequency of 700 hertz. Now this is an interesting problem. We're going to look at something a little different. Let's say we have an ideal filter in the digital domain. This would be a discrete filter, right? H of e to the j omega. Let's say it's a filter that passes frequencies from 0 to 0.4 pi radians per sample. Now, since it's discrete, it has to repeat every 2 pi, so this is going to repeat again and again and again. Now, we know that low frequencies are the frequencies close to 0, high frequencies are frequencies close to pi, so this is going to be a low-pass filter. And what it tells us is this. We're going to sample a signal, pass it through this ideal filter, and reconstruct it again. Now we could look at all of this as an equivalent analog signal, or an equivalent analog filter. And we want to find out what is the cutoff frequency of that equivalent analog filter. Now actually, this is actually done a lot in practice. Instead of using an analog filter, in many applications, the signal is sampled, it's filtered digitally, then it's reconstructed. And it turns out you can do it on a chip, and in many cases it's actually cheaper than implementing an analog filter. But in this case, let's say we have this filter, and we want to know what is the frequency of what cutoff frequency it is. Actually, what they ask us is what sampling frequency should we use if we want the system, if we want this equivalent filter to have a cutoff frequency of 2500 hertz. Now, this is just a play of equations, right? We know the relationship between a continuous time frequency and the discrete time frequency once it's sampled. This is our equation. Now, we want 0.4 pi radians per sample, which is the cutoff frequency of the digital filter. We want that to be equal to a cutoff frequency of 2500 hertz. Now 2500 hertz, of course, is 5000 pi radians per second. And this is what we want. We want this to be equal. Now, and what we want to find is the sampling frequency so that these two things are equal. And we find that the sampling frequency that we should use is 12,500 hertz. In other words, if we sample at 12,500 samples per second and we pass the signal through this, it would be the same as if we had used an analog filter with a cutoff frequency of 2,500 hertz. Let's do one more, and let's make this a little more practical. Now let's say we have a signal in MATLAB. And we can make filters in MATLAB, of course. Now it says we have a speech signal in MATLAB, and we want to put it through a low-pass filter. We want to eliminate all frequencies above 2 kilohertz. The speech was sampled at 8 kilohertz. What should the cutoff frequency of the discrete filter be? Again, this is the equation that relates before and after sampling. And so in this case, we know the original cutoff frequency, 2000 radians, or 2000 samples, 2000 hertz, multiplied by 2 pi to get radians per second. The sampling frequency is 8,000 samples per second. So we divide this and we get 0.5 pi radians per sample. So the cutoff frequency of the discrete filter that we're going to design or could design would be 0.5 pi radians per sample.